of Pharmaceutical Sciences at the College of Pharmacy at Western University. He has a joint appointment with Charles Drew University. He obtained his bachelor's degree in pharmacy from the College of Pharmacy, Kabul University in Kabul, Afghanistan in 1981. He's our only Afghanistani American faculty member we have at Charles Drew. Immediately after graduation, he was appointed as an assistant professor in the Department of Pharmacodynamics, but had to leave Afghanistan due to the war in 1985. He was a refugee in Pakistan when he came to the United States in 1987 and joined the faculty at St. John's University. I'm sorry, came to St. John's University to obtain his MS degree. He was working as a teaching assistant and eventually received his a PhD from St. John's University. He came to to California in 1990, was at UCLA, and then joined UC Irvine, and then joined UCLA as a postdoctoral fellow in 1996. He had a KO1 award. He joined Western University in 2003 and was funded with an R01 grant on drug abuse from National Institute of Drug Abuse. He's been awarded Teacher of the Year and has multiple faculty service awards. And in 2015, he was Provost Scholar of the Year. He was on study sections, and he is quite active in research related to substance abuse. And today he's going to be talking about animal model of drug addiction, operant conditioning, place conditioning, and two bottle choices. Thank you, Kabir.
Thank you so much, Ted, for such a detailed introduction. Uh, so, good morning, Estelle. I think it's still morning. I hope you guys are not tired, but I'm trying to see if I can make it a little bit fun at the same time, go back and forth, and show you some videos, clips, so you get a little bit better to get to know the system, the models better, as much as I can. And the first model I want to talk about is the operant conditioning, which Dr. Simon actually touched to a great extent there. He didn't talk about, he basically he focused mainly on the decision making as well as on the punishment and those things. But you can use this model. Actually, this model is um, Skinner, when developed this model, he came up with, like consequences of action influence our behavior. That's the idea behind it. Like, for example, you study hard, you write several grants, one of them will get funded, and then you keep writing grants. If you write bad grants, you will not get funded. So that is like a kind of a incentive for you to be able to write a good grant in order to get funded. So that is, you know, that is the basis for reinforcement. The reinforcements in terms of drug addiction has two aspects: the positive reinforcement and the negative reinforcement. So when we say reinforcement, that means something you do that will allow you to repeat the same task because of, you receive either reward or you want to avoid the unpleasant consequences. For example, your car insurance, drive safely each year, your premium, I assume, will go down. I mean, although it doesn't. But if you're not a safe driver, your premium each year will go up. So in order to avoid that, you try to drive safely. That's what an example of a positive and negative reinforcement would be in real life. But in animals, you give him a rewarding agent. Let's say that rewarding agent could be a natural rewarding agent or could be a drug reward. For example, you can give him a food pellet, which Dr. Simon showed, or you can give them a sweet solution. They love it and they keep drinking it. And if you give him, the drink for a while, and then, or you give him, high-fat diet for a while, and then you take that high-fat diet from these animals, if they are addicted to high-fat diet, if you take it away, they will go through negative affect. So basically, they'll show depressive-like behaviors, like humans. They will show anxiety-like behaviors, similar to humans. For example, if humans are addicted to opioids, and if you take the opioids away, they will show these signs of withdrawal, and that's what basically the reinforcement is. So you can also use the operant conditioning to study punishment. Like for example, you give a rat or a mouse a sugar solution, but you, as Dr. Simon mentioned, you also associate that with a foot shock. So, depending on whether animals take the risk or they don't take the risk, they might avoid it or they might keep doing the same task. Let me go show you like a short video clip. So this is basically a mouse performing the task in an operant conditioning to receive a sugar solution. Let me see if I can share that video. I hope I can. Okay. Do you guys see this mouse?
Yes, yes.
Okay. So you can see that the right side there is a lever right there, and then there is a nose poke area. When the mouse is pressing the lever, there is a sugar solution is delivered there. And you can see that each time there it's pressing the lever, it gets like a 20 microliter or 30 microliter of sugar solution. So initially you train these animals, and then they start to learn the task, and then you can modify the task to study different aspects of addiction. Let me just go back to the PowerPoint. Stop this. Okay. So basically, the initial part is the handling and training, so that the animals, like you're shaping the animals to learn the task, to do the task you're expecting the rat or mouse to do the task in order to receive the reward. And then after that, you use a schedule of reinforcement. That is a schedule of reinforcement could be a fixed ratio. A mouse could press a lever one time and they get a reward after one lever press, or you could change it to 10 presses. After 10 presses, that mouse will get a reward. So we call that fixed ratio. You might have seen it, fixed ratio 1, fixed ratio 5. That means there is one, if it's fixed ratio 1, that means it's a one lever press associated with one reward. If it is FR5, then the mouse has to press 5 times consecutively in order to receive one reward, one time the reward. And then there is another procedure which like mainly used for study of drug addiction is progressive ratio, because that assists the motivation. Whether a mouse or a rat will work, like you guys saw that even if you associate the reward with the foot shock, the rat will keep doing. Some rats will keep doing the same task. So this is the kind of the same idea. You increase the workload on them in order to obtain the same reward. So what you do is basically you increase the number of lever presses. So for example, if R1, if R2, if R3, if R5, if R8, if R9, if R 16, something like that. And then you go to tell the animals give up, and that's the break point in drug addiction. So this is you can use the operant conditioning to study drug reinforcement, as well as drug self-administration. That could be, as I showed, you can assess oral self-administration of a solution or a drug like alcohol, for example, or you can, connect an IV line, and then the mouse or the rat will perform the test to get an IV injection of cocaine, opioids, nicotine, and other addictive drugs. So you can assess both reinforcement and self-administration, um, and you can study different aspects of addiction. You can, for example, look at the developmental stage of addiction, where the subject will start keep pressing the lever in order to receive rewards. And you can, for example, assess the effect of certain drugs during the acquisition. You can give a drug before the animal is starting the task, so that way you can see that whether there is influence, increase or decrease in the ability of animals to perform the task. You can assess that, or you can study extinction, which is basically you train the animals to, for example, self-administer solution of sugar or intravenous injection of cocaine, and then you switch the cocaine solution to a saline solution. So the rats quickly learn, like they learn very, very quickly that, I'm not stupid. You give me something, I should work for it. I'm not going to do it. And then you can see that self-administration will reduce to back to almost basal levels, and they may not even perform. And then you can also do use this paradigm to study relapse, craving, and relapse, so that you can do a reinstatement, and you can expose the animals to the same drug again, and then you can see that they will start doing the task again. And also you can expose animals to a stressor. That stressor could be, a drug like, yohimbine, for example, which blocks alpha-2 and activates the sympathetic system, the adrenergic system, and that can elicit reinstatement. Or you can just use, like other stressor, foot shock, force swim and restrain, and other stressors. So especially this part, the reinstatement aspect of addiction is really the main problem in treating drug addiction, is the treating craving and relapse. And a lot of like research or in this aspect, to see whether there are some drugs can affect the reinstatement, and that can be used for drug addicts, because during accusation, like you're basically using a naive subject and you're exposing them to drugs in order to develop addiction. So at this time, if you even prevent this process, it may not be, it's only used as a preventative. That medication will be used only as a preventative measure, but it may not have any clinical usefulness in drug users. For example, in drug users, there are certain changes in the mesolimbic dopaminergic neurons. There are certain changes in the corticolimbic glutamatergic neurons. They lead to these behavioral changes. And a drug working at this phase of addiction may not be useful for that phase of addiction. So therefore, studying this process might be useful, because a lot of people, they want to, like stop taking drugs, and therefore finding any medications that can help with this process, facilitate extinction, inhibit reinstatement. That might be clinically very useful medication. Okay, so this is like a study where we looked at sugar self-administration in two group of mice. One, they had mu receptors, and the other group didn't have the mu receptors, because the mu receptor, the opioid system, is long known to be involved in natural reward as well as drug reward. So we wanted to see if there will be any impact of mu receptors on sugar self-administration. So we trained animals to self-administer sugar solution. Initially, we started with 2% sugar, and then you can see that both lines of mice of both genotypes, they are performing the task. They self-administer, and you can see that this is on the y-axis, lever presses, how many times they lever press to get the sugar solution, and it's only 20 microliter of sugar solution. So they like perform the task to get about like 1 ml or so, and then they increase it when you increase the concentration of the sugar. And then each time there's a bump, and that bump is because what we do is we do the experiment on Monday night, Tuesday night, Wednesday night, and Thursday night, and then Friday night, Saturday night, and Sunday night they're off. Basically, we don't do this experiment continuously, but some other labs, they do that continuously. And then when we put them back on a Monday night, you can see that it's probably, I assume it is deprivation induced increase in intake, that, and then the animals initially they show that bump, and then they kind of like don't show that like a rise, and because they know that I'm gonna drink this much and that's good enough for me. And the only thing we saw is when we increased the concentration of sugar to 8%, we saw like a downward trend, but we didn't, I mean, we saw it here too, but like but wild types, they kind of trended upward back again, whereas the knockout seemed to be going even more. It would be nice if we continue this type of experiments for longer, and these are all just unpublished. One of my graduate students did this experiment. The other model we like it's widely used in study of drug addiction, although it is not like studying addiction, but it is used as a model of reward, basically. So in this, as the name states, conditioned place preference. You condition a mouse or a rat to prefer one place over another place. Okay, so let me just go back to show you what I'm so sorry for going back and forth, but so these are actually the CPP chambers. Do you see the video? So as you can see that these are med-associated CPP chambers, and then there are three chambers basically in this apparatus. The middle one is the central neutral chamber, and through this one, the mouse will have access to both conditioning chambers. One is on the right side, one is the left side. The left side is white, and the right side is black color. And then they also have tactile cues, which you cannot see it, unfortunately. So they, in order to, because animals like to stay in the dark side, so they put rods in the bottom of these cages, whereas they put mesh on the white side. So sorry, yeah, a white mesh on the white side. So that way, the animals, they don't show initial preference. If they go to the dark side because of the rod, they don't feel comfortable. They kind of, like, don't stay there. Whereas in the white, so over time, when you expose the animals to these chambers, you don't see much of a, like a initial preference. Sometimes there is a small preference for the dark side, but we adjust the baseline basically to make sure that it's not there anymore. Let me go back to PowerPoint presentation. Okay, so in the condition place preference procedure, there are three phases of this. So this is a model of drug reward again, and some people also consider it as a model of seeking behavior, which I will discuss it later. You can. Although some people are critical of this model to study drug addiction, but I think it's useful to study different aspects of addiction without doing any surgery or any other manipulations. So there are different phases of condition place preference. It's a preconditioning where you test the animals. Basically, you open there are guillotine doors. They kind of separate the conditioning chambers from the central metal chamber. So on the first day, you remove those doors, and then you put the mouse in the middle chamber, and then the mouse will keep moving, because they, animals, or especially mice and rats, are exploratory in nature. They just, like, move around. You can train them, you can habituate them to the chambers if you want to, but there is no need for that. In most cases, people don't do that initial habituation phase for condition place preference. So you can measure it for 15 minutes, and then the amount of time they spend in each chamber, you record that. It can be done manually, or it can be, um, automatic. You can have the system, and then once the preconditioning is done, the next day you close the doors, and then you start conditioning them, the animals. And during the conditioning phase, so you inject, or you can expose them to, some treatments, where, for example, exposing them to nicotine vapors, for example, or alcohol vapors, if you want to, and you put them in one of those two side chambers, and you consider that, because they're receiving drug, you consider that as, you can call that drug pair chamber, drug pair chamber. And then you, in the afternoon or the next day, you can expose the mouse to a control, a vehicle, which you use. Either you use the saline, or you use water vapor, whatever you use, you can use that as a control and expose animals to that, and then put them on the other side. So if you do these conditioning, and if the drug is a very powerful rewarding agent, a high dose of drug should be able to induce a condition place preference even after just single conditioning. But if the drug is not a very powerful rewarding agent, or you use a very low dose of the drug, you have to repeat this alternate day conditioning for a few more days, for, like 10 days, 20 days, whatever. That it's like, you can look at the literature. And for example, for opioids, or cocaine, amphetamine, one conditioning is good enough. But you can do also several conditioning, up to 10, 8 conditioning, 4 of saline and 4 of opioids, and that 4 of morphine or oxycodone or something else, and that should yield a very good CPP response. Then after the conditioning phase is done, 24 hours later, you test them for post-conditioning place preference. And this is actually a study where we did, as you can see that, this is the baseline. BL stands for the baseline. And then you can see that when we test them before any conditioning, the animals do not show any preference towards these chambers. Like almost equally, they spend the amount of time in both chambers. When we start conditioning them, they receive 2 drug conditioning and 2 saline conditioning, or 2 vehicle conditioning, you can see that there is a drop in the vehicle pair chamber, and that there is a small gain in the drug pair chamber. Decrease in vehicle and an increase, somewhat increase in the, although this is not significantly different from this, but it is significantly from the vehicle pair chamber time spent. So that's the y-axis is the amount of time the animal has spent. So again, similar to day 1, when you test them, and you open the door after you condition him, and then you open the door again and put them in the chambers on this day to see how long they go. As you can see that this drug is rewarding agent, and therefore the animal will tend to spend more time in the drug pair than the vehicle pair. And if you keep conditioning for a little bit longer, you can see that even in the drug pair, there is a kind of gain, although there is also a small gain in the vehicle pair chamber there too. But overall, there is a significant difference there. So this model can be also used to study aversion. If a drug is aversive, the animal will do the opposite. So, which is, it's in this study, which was done by Dr. Sahed, which is among the audience, I assume. And so, if you test them for baseline on day 1, there's not much difference, and then you condition him for 4 days to saline to drug, and you can see that still there is a small thing changing. But when you continue it for another 2 saline to drug conditioning, you can see that there is a decrease in the drug pair chamber and time in the drug pair chamber, and there is an increase in the vehicle pair chamber. So showing that the animal doesn't want to go to the site they receive the drug. So this drug is aversive. A very simple example of this could be, if you give opioids, for example, if you give morphine, oxycodone, or anything, they show place preference. But if you give an opioid antagonist like naloxone, they will do the same thing as you see here. But they will even show at much earlier time point. Even one single naloxone injection is sufficient to induce aversion. And this drug was not a very powerful aversive agent, but it is showing after like a kind of longer term conditioning CPA response. So you can use the same like this also for different phases of addiction, although people they say like it's not used as a model of addiction, but you can look at extinction, because this is also all these models I'm talking about it's based on learning. In this case, the animals will learn, associate the subjective effect of the drug with the context, whether that context is a black chamber with rot tactile cue, or a white chamber with mesh tactile cue. So they associate those two, and then whether the drug is they like the drug or they dislike the drug, they tend to prefer that chamber or they avoid that chamber. And you can study accusation phase of, a place preference, and you can do also extinction. This model is being used as a model of extinction also, and reinstatement as well. So if you turn expose animals to like repeatedly test them, which is called natural extinction, the animals eventually will not show preference or avoidance towards these chambers. They will become like similar to their baseline. But if you do forced extinction, what we do in the forced extinction, we actually inject animals with a vehicle and expose them to both chambers. So now they're not, feeling that subjective effect of the drug to associate it with it. So over time, they lose that memory. I think it is not the loss of the old memory, but they develop a new memory, which, these two things are the same. Why I should go to one side than the other side? And eventually the response gets extinguished, and you can reinstate it, and you can expose the animals to the drug, and then boom, they go to the side if that's rewarding. If it is aversive, they avoid that drug pair chamber. And you can do the same thing with stress. Two bottle choice is another paradigm, and that is widely used for treatment of, for studying, for example, alcohol preference and self-administration, and nicotine and self-administration, nicotine preference, and looking at the impact of different genes and receptors, proteins on that. So basically, you can use it to study self-administration. If you're studying, like alcohol self-administration, nicotine self-administration, or sugar self-administration simply, or you can also study drug preference. If you study drug preference, for example, alcohol preference, so you just measure how much the animals will drink alcohol and how much they drink water. Basically, in this model, you have inside the cage, you have two bottles. One bottle will be inert substance, like their water bottle. The other one, you add something into the water bottle. You can add sugar, you can add alcohol, you can add nicotine, whatever you are interested in. So there is an habituation period here also. In this period, you basically expose the animal to two bottles, because normally, in animal cages, you have one water bottle and a food dispenser. In the study of two bottle choice, instead of one bottle, you add two bottles there, and both of them during habituation will containing water only. And then you can later on switch. You can do that for a couple days and maximum for a week. And then you do a test period where you remove one of the water bottles on the right side or the left side. You can take it away, and you insert another bottle containing alcohol, sugar, or any other drugs you are interested in, and drug self-administration or preference. And this is one study where we looked at nicotine self-administration in the two bottle choice. Nicotine is kind of, has taste aversion. So taste, when you increase the concentration of nicotine, even with 20, we put 20 microgram per ml solution of nicotine. The animals, which, like initially they were preferring this side over this other side, the moment we put nicotine on even the preferred side, these animals, you see that the first day they are okay. The second day they taste nicotine, they say, it is not different than the other side. So basically, there is a little bit of increase for the other side, and it's a huge drop in this side. So that difference disappeared basically when we increase. And then when we at higher concentration, it seemed to be kind of in a more or less the same pattern. Whereas when we studied, we were interested in the role of PCAB, which is a peptide. It activates adenylyl cyclase in the pituitary. That's the reason the name stands for pituitary adenylyl cyclase activating polypeptide. That those knockouts, despite the fact they didn't have initial preference, when we gave them access to nicotine, boom, they stayed the first day of nicotine, they drank a lot of it, and then they seem to be staying up still compared to the water side. And then you can see that actually, like compared to here, the water side, they don't go to the water side that much, they don't drink as much, but they basically measure the nicotine. And then if you increase the concentration of nicotine, that preference doesn't change at all. Actually, if anything, that becomes more robust. And even you go to 80 microgram, which is like really aversive solution, they don't show any aversion until you see that slowly they are building up, that showing somewhat aversive response to this. So you can use this to study the impact of certain genes. For example, we looked at these knockout animals. They're missing this gene encoding for this particular peptide. They showed reduction. So we suggested that this peptide might be involved in the aversive effect of nicotine. And in fact, when we did study, we did condition placed preference, we found out the aversive effect of nicotine is blunted in these mice, which was also published in the same paper. And the other model, which is used, I don't know, how's our time?
You have till noon, but give a couple minutes for questions. So
Okay.
it's
So
it's 11:50, so about 6 or 7 minutes still.
Okay, so locomotor sensitization referred to as an enduring increase in locomotor activity, and this is this also some people consider it as a some aspect of a model of some aspects of addiction. We basically published a couple papers using this model and studying. And so basically, this model, when you treat animals with cocaine, the first day you get an increase, or you inject morphine in mice, they show increased locomotor activity, and that increased locomotor activity is growing day by day. And I think I have a let me just quickly show you that study where I did at UCLA. Actually, when I was at UCLA with Chris and in Dr. Nigel Medman's laboratory, I did this study. This was part of my Q1 award. So we injected animals with the vehicle followed by saline, or we injected vehicle followed by cocaine. And you can see that cocaine increases locomotor activity. This is the first day when we gave him this injection. And then there was a peptide, it's called orphanin FQ or nociceptin, which earlier in the lab we found out this affects the dopamine system. It reduces the dopaminergic neurons. It decreases the level of dopamine in the nucleus accumbens. And also I showed that reduces the ability of cocaine to increase dopamine. So if the action of cocaine is basically blocking the dopamine transporter, by blocking the dopamine transporter, it increases. So if you turn off the dopaminergic neurons, there is decreased amount of dopamine coming out. So cocaine cannot do much, and therefore if you inject that drug before cocaine, you reduce the action of cocaine significantly. And then so this is their day one response. This is day two response, and then you can see that still the drug is able to reduce the action of cocaine. And this is the day three response. So you inject cocaine, like every day for 3 days, and then you give some time off for the drug for sensitization to develop, and then you challenge the animals with. Do you guys see this?
No, Dr. Lufti, we're only seeing other folks.
Oh goodness, I'm so sorry. I forgot to
That's okay.
I forgot to share this, huh? Maybe that's the reason.
There we go.
Okay.
Perfect.
So this is the one I was talking about. So if you inject animals with vehicle and then you give them, like these open bars, the open triangles, you give them vehicle followed by vehicle ICV, you give them in the ventricle injections, and then you give them IP injection of saline. That's what you get. And if you give a vehicle before you give cocaine, you get this response with cocaine. Cocaine increases locomotor activity. And then this peptide, orphanin FQ, reduces the action of cocaine significantly on day one, day two, and day three. And then when you inject them, give them some time, like a week off, and then you come back and you do the test. I would like you to look at here. So, and here we, like you remember the first day we gave animals vehicle saline and vehicle cocaine. So let's compare those groups first. And now here on day 8, we inject everyone with cocaine, all of the animals. And cocaine was given around this time. The animals, they received vehicle followed by saline. You see that this is a lower dose of cocaine, by the way, compared to day one. Day one is 15 milligram, here is 7.5, half of the dose. You can see that this dose produces a nice increase in locomotor activity. Animals previously received cocaine. When they were challenged with this low dose of cocaine, they showed a much greater response. And that's what locomotor sensitization is defined as, an enhanced locomotor activity upon repeated administration. And it's intermittent administration. If you repeatedly give them, like it's all the time infusion, then the response will show actually tolerance, if anything. And then you can see that the peptide actually didn't affect the motor activity, and the peptide along with cocaine, you didn't get that sensitization. This was, like a kind of, like the paper that we published in Psychopharmacology in 2002 when I was at UCLA. So you can use this as a model of addiction, and we also not only we blocked sensitization in this our other paper, we were able to actually reverse sensitization, which is showing that this peptide could be during sensitization. If you recall, I mentioned that there are changes in the dopamine system and changes in the mesocorticolimbic glutamatergic neurons. And those changes are responsible for the behavioral changes. And in fact, this peptide shows to actually reduce those behavioral changes. Although we did not look at neurochemical changes and those, that is something we could probably do in the future. But I just wanted to explain it to you that this peptide, orphanin FQ, not only blocks the development, but also reverses reverses locomotor sensitization. Right now we have a U18 grant where we are actually now looking at the small molecules acting on this orphanin FQ receptor, which is called NOP receptor or ORL1 receptor, to see if we can use those compounds to induce the same effect, because this peptide we have to give him directly in the brain, because you cannot give that drug orally, and hopefully we're seeing if we can get the same effect with the small molecules that can be used for treatment of cocaine addicts. So that's all I wanted to share with you. There are other models, but there was limited time, so I just focused only on these models. I hope you enjoyed it.
Thank you, Kabir. That was an excellent overview. Do we have any questions? I also want to remind people that we have a breakout discussion session at 2:30. If the speakers can come back for that, and then we can have some more discussion at that time.
Okay.